Okay, off we go. So real quick, again, before we get back into the material, just want to remind y'all that we are going to begin with attendance counting by way of attendance quizzes on Wednesday. That's the plan, anyway. So, fingers crossed I can get, everything, all the organizational stuff done that I need to get done. It'll happen tomorrow. That's the plan. That I'll have the Canvas site created and at least the first few attendance quizzes set up and ready to go. And so what y'all can do, if you haven't already done so, in fact, I'm practically certain you already have, but get the Canvas app on your phone. Make sure you're comfortable with how to use it, how to log in, how to stay logged in, whatever, right? All that stuff. Then you should be largely ready for the announcement that'll come on Tuesday. With the announcement on Tuesday, I'll say something to the effect of, I put up a practice quiz so that you can see exactly where to go. Make sure you know where to go in this course's Canvas site that will have been created by then. Make sure you see how the quizzes work. See how to hit, because I don't see the student end, right? But you need to make sure that you know how to submit, right? It's not good enough to just enter the correct answer. You have to actually hit submit and then make sure that you get credit for the submission. Right? Anyway, email coming out tomorrow, hopefully, with all of that stuff. And this is just a heads up. Okay, all right, so back into the math. Here's what we were doing last time. We were talking about spherical coordinates. Let's see, let me get into the correct mode here. Yeah, there we go, spherical coordinates. We talked through how they're defined, a lot of little details, right? But basically this is the picture of how we think about rho, phi, and theta, how I like to think about them, and further details over here on the right. And we talked through how to find the conversion formulas. And we talked through some examples of many different ways that you can represent the same point with spherical coordinates. And what I'm sure you noticed, it's geometrically challenging, right? There's you got to think about things. I got to turn around and look upside down. It's very, very confusing, right? So give yourself the practice as needed to make sure that you can think about spherical coordinates, every which way. Okay, picking up from there. This, I think, is a lovely little observation. I really like this. Again, I did not think about this myself. Somebody pointed this out to me. Okay. So, what is pretty clear, and what you may have already noticed, is that spherical coordinates, the angles, right, not terribly different from longitude and latitude. Right, presumably y'all have seen longitude and latitude in some earlier context. But notice that if we set up the globe with the center of the Earth at the origin, with the North Pole at in the positive part of the z-axis, and with the prime meridian in the direction of the positive part of the x-axis, arbitrary but reasonable, I think, way to set up the globe in an XYZ system. You'll notice that east longitude is theta. All right, it's the same thing. How about that? What are the odds? And then notice that north latitude. Okay, now that's not what phi is, but you will notice that phi, being like so, right? Phi is closely related to north latitude in that they add up to pi over 2. Right? They're sort of complementary to each other in some sense. And then now, if we're thinking about a particular location, if we're thinking about a point there on the surface of the Earth, and if I want to think of that point as a vector in space, well, what is the magnitude of that vector? Well, the magnitude of that vector is the radius of the Earth. Right? Which is, by the way, we're going to approximate the Earth as a sphere, which isn't quite right. Fun fact, not only are there mountains and valleys, but also the Earth is a little bit oblong. Right? It's a little bit sort of pancake. And that's because it rotates, and the rotation creates a air quotes, centrifugal force. And the punchline is it's the distance between the poles is a little bit less than the distance between opposite ends of the equator. It's something like 20 miles. It's surprisingly quite a bit. Okay. Anyway, but on the scale of the thousands of miles that is the general radius, it's not such a big deal. Okay, so here's the big idea then, and that's what I think is super clever. If you look at 2 points on the surface of the Earth, how do you find the distance? Right? Reasonable question. Airlines very interested in this question. Right? They need to know how much gas are we going to burn. Now they have other considerations like the jet stream and stuff like that. But nevertheless, finding the distance between 2 points on the surface of the Earth, pretty important, pretty natural question. So if you try to do that with longitude and latitude sort of directly, it gets real confusing real fast. You certainly can't do it by looking at a map, right? At least not a flat map, right? All flat maps are bad in some very real, very meaningful sense. They always distort distances at least a little bit, even the good ones, right? So what are we going to do about this? And here's the great idea, super simple idea. If you know what points you're talking about, presumably you know their longitude and latitudes, which we can then convert to spherical coordinates, which we can then convert to rectangular coordinates using the formulas on the previous page. Once you know the rectangular coordinates, now you know these locations on the surface of the Earth as vectors in rectangular space. And now the question of finding this distance, S, pretty much boils down to understanding, well, how can I find this angle between those two vectors? Now you got to think about, obviously the radius of the Earth matters, right? But once you know that angle, you're in business. And how do you determine that angle? Well, that angle is closely connected to how you would compute the dot products of those two vectors. Right, so flashback again to linear algebra. Dot product of two vectors gives the product of the magnitudes times the cosine of the angle. That's exactly the angle we're looking for. So this is kind of a roadmap. Now there's a lot of little details in there. You'll almost certainly have to use a calculator, right? This is not to suggest that you should be able to compute, the sine and cosine of weird angles like 21.4 degrees, stuff like that. No, absolutely. You've got to use a calculator, of course. But this is the roadmap that'll let you start with longitudes and latitudes and end with a very accurate computation of what that distance is. So I think that's kind of wild, kind of fun. Okay. All right. Again, let's be quick about this one, but if you want to convert the equation, a rectangular equation like this, into a spherical equation, and we will have a very compelling need to do this later in the course when we get to integration techniques. Very powerful integration technique is going to require that we do this sometimes. So how do we turn a rectangular equation into a spherical equation? And again, just like with cylindrical, just like with polar, you pretty much just plug in the conversion formulas. Pretty straightforward. The one little slick move you'll notice here is that I have sort of cranked out the square first before I plug in. No big deal, right? But if you do that, then what you notice is that this very convenient conversion formula, identity relationship between the variables in these different coordinate systems, pops up, allows you to save yourself a lot of trig. Right? You can get it done without making this clever observation, but when you have the opportunity, it's a real effort saver. So I'm a big fan. Okay. And then it's all over with the shouting. How are we doing? Everybody on board? Okay. Everybody have a good weekend? Anybody else go to the football game? All right. Good. All right. Yeah, I was there. Sunburn. Sorry? I'm going to give you an alternate take, and that is we held our own, right? I mean, not at the end, right? But for a long time, I mean, we had them worried I know because I was sitting with my friend who is an Illinois alum, and he was worried. Right, so we gave them a run for their money. They're a ranked team, so I view this as a good sign. I think we're going to have a good year. Okay, so this is a fun little conversation that we have to have. At first glance, this is going to seem like an outrage. Ultimately, I'm going to try to persuade you this is not a big deal, and in fact, this is arguably reasonable. But not everyone agrees on what to call the various variables, the various coordinates in these alternative coordinate systems. They don't all. Some books use different conventions as to what's rho and what's phi and what's theta and what's r and etc. There's some compelling need for this. So, for example, rho that we're using as the kind of what I'll loosely call the radial coordinate and spherical coordinates also gets used for charge density in a lot of physics and engineering contexts. Right, so that's a potential source of confusion. So the big point is this right here. You have to be vigilant. You cannot just go around assuming that the formulas that you see here or the formulas that you see in any other context, that you can just, ride those on into the sunset and always use those, because you're going to find yourself in some context where in that context they use a different convention of what the variables are called. Now, this seems, again, at first glance, it seems like an outrage, right? Come on, we got to get on board, and everybody, let's all do the same convention. Pin that thought. I'm sure y'all are accustomed to the idea that if you're talking about rectangular coordinates, we call that one x and we call that one y. Right? We're all pretty accustomed to this. But, if you take like an econ class or if you're doing some engineering and you need to understand how some, engine efficiency, how that depends on the angle of the rods of the engine, or I don't know, something like that, right? Then maybe this is going to be called alpha and this is going to be called E. So they're not X and Y anymore. Right? Now, is this an outrage? No, this is a necessity. Right? We have to be able to be flexible about what we call our various axes, aka our various coordinates. Right? And you're always responsible, and whatever the context is, you look at a picture and you see that there's names to the axes. You're always responsible to look and make sure that you're correctly understanding what names are being used to describe what coordinates. So I make the observation that since we do this all the time anyway, it's really not such a big ask that we always be vigilant about this kind of thing. Okay, so now before I get into I'm going to come back and talk about all that stuff, but I want to show you specifically what you are likely to see elsewhere. So this right here is a picture of another very, very common choice. You'll notice that what we have typically previously called rho, in this convention it is called R, which is not only not the same letter, but it's the letter we use to represent something else. Right? Namely this distance down here. So, that's, heads up. Right? Be careful about that. And then, one of the really frustrating ones, notice what we have in the past called phi, in this convention is called theta. And what we in the past have called theta, in this convention is called phi. Right, so heads up on that one. You got to be careful about that. Right. So, by the way, for whatever it's worth, this is the convention that is common in physics circles. Right. So, you're going to be taking physics classes, and I'm not exactly sure what the conventions are in engineering. But anyway, one way or the other, you are going to see some these other conventions in some context or another. Notice, of course, if you change the names, that also changes the conversion formulas. Okay. All right. Fine. Okay, so various bullet points here. And we've already kind of talked about this, but don't get attached to a single convention. That's not reasonable. You can't. You have to get on board with whatever the convention is and whatever the context is that you're doing some work. So that's just a word of warning. Now, the convention that I'm going to use mostly in this class is the convention that's used in our textbook. I think that's a reasonable decision to I feel like I don't want to say we have to, but I think there'd be a lot of disadvantages, right, if we didn't mostly kind of stick with the book's convention. So Kali seems pretty on board with the rho phi theta convention, so we're going to mostly use that. That said, whatever your context, and this applies outside of this course just as well as inside of this course, if you are asked in an exercise, by the way, maybe there will be an additional homework problem, right? The additional homework problems are not written by Kali, right? Maybe there will be an exam question, possibly on my exam, right? Possibly on the final exam, right? But if there is an established convention, you have to stay on board with that convention in your work. You can't say, oh yeah, I don't like that, I'm going to use the rho phi theta. You can't do that. You've got to stick with whatever the established convention for the problem is. Does that make sense to everybody? I mean, it would just be unthinkably confusing if we didn't have a policy on this. Okay. All right. If there is no established convention, right? So if the question says something like, compute the blah, 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 and then you decide, independent of the statement of the question, you decide that you want to use spherical coordinates, which, by the way, that's very often how stuff works, right? Then you have to make your choice unambiguously clear. Right? You cannot assume that your readers will know exactly what you mean by theta. Right? So now, how do you make your choice clear? I suppose you could draw a little picture like this. I don't think that's the efficient way to do it. I think the efficient way to do it is to write something like this. This is what I'm going to encourage. By the way, it is close enough to a standard convention that we're going to get on board with it in this class, that whatever you list first is that, what I'll call the radial coordinate, right? Whatever you list second is what I like to call the vertical angle, right? So phi in Kali's and mostly our convention, right? And then whatever you list third, let's see here. Whatever you list third, what is commonly called the horizontal angle, sometimes called the trivial angle, sometimes called the azimuth, which is pretty antiquated terminology. But I think to me, I just call it the trivial angle. But whatever you list third is understood to be the trivial angle, and again, that's in our typical convention, that's theta. By the way, the reason they call that the trivial coordinate is because when you start working out like really, really hardcore, difficult physics problems in spherical coordinates, which, by the way, is a powerful, powerful tool for understanding lots and lots of real physical problems. The way the trig and the algebra work out for this angle just tends to be way, way, way easier than how the trig and algebra works out for this angle. So because algebraically everything kind of tends to work out simply and nicely and naturally, almost trivially, you might say, and very often literally trivially. That's why we call it the trivial coordinate. Okay. Okay, so that's, I think, the easiest way to establish your convention, so you can just write spherical rho phi theta, and now I know exactly what you're talking about. You're using the Collie convention, the convention we've been using in class up to now. No problem. If you were going to use this convention down here, you would say spherical r, theta, phi. And again, you got to say so if it's not been established elsewhere, like in the statement of the problem. How are we doing? Is everybody on board? All right. So a little bit annoying, but ultimately, I think not such a big deal. Is everybody good? Okay. Yeah.
So you can do whatever as long as you define it. Like by
if there is no established convention in the question, that's right. If you're the one that decides to use spherical coordinates, or if the question says use spherical coordinates but it doesn't give any indication of the convention, then yes, you get to decide. Yep. But again, you have to be unambiguously clear. Yeah, that's right. Okay. So a quick thing about standard basis vectors. Now again, we've talked about these previously. I'm sure you all have seen IJK. Again, I like the E1, E2, E3 convention. It's more bulletproof against possibly having more dimensions that you might have to deal with. IJK kind of becomes a problem if you have more than 3 variables to deal with. So these are, in fact, just the rectangular standard basis vectors. There are standard basis vectors in these other coordinate systems. The problem is they don't work as well. They don't work in as many different ways, right? What they do is, as I have indicated here, given a point, given wherever you might happen to be, we're going to start by thinking about polar coordinates. All right, so let's look at polar coordinates here. We can talk about the vectors that point in the direction where you're increasing just one single coordinate. All right, so for example, from this purple point that I have there, I can talk about what happens if I hold theta constant and then increase only r. Well, I'd be going that direction. And so that's what we call E sub r. And then I can talk about, what if I were going to hold r constant? Now I'm going to increase theta while r is being held constant. As I increase theta, what direction am I going, right? What is the direction of motion, instantaneously? Right? I mean, obviously it curves around, right? But at the instant where we're at that point, I'd be going that direction. Right? So these are called the polar standard basis vectors, and we write them as let's see here, these vectors, we write them as ER and E theta. And I think a good little exercise, you don't have to do this, but I think it's a good exercise. You can persuade yourselves that these are the formulas for those polar standard basis vectors. Did I see a hand somewhere? No? Okay. Nice little exercise. So likewise with the other coordinate systems, and these are maybe, especially the spherical, a little bit more geometrically challenging, right? But I claim that these are what these spherical standard basis vectors look like. Now again, you just have to think to yourself, by the way, I'm using the Collie convention here, right? You notice rho phi theta, right? By the way, anything you see in my notes, assume that they are in the Collie convention unless explicitly indicated otherwise. That's a good little exercise to think through. Okay, well, if I'm at that point, what does happen if I hold the other variables constant and increase only one of the spherical coordinates? And these are they. And then another good exercise that I encourage you to give a try. These are the formulas for those spherical standard basis vectors in terms of the rectangular coordinates. So a couple things to notice. First of all, notice they're not constants, right? They're formulas. There's no formula for E1, E2, E3 in rectangular coordinates. They're constants. No matter where you look, E1, E2, and E3 are always the same. Not for these other coordinate systems, right? The spherical standard basis vectors are not, they change depending on where you are. which is a little weird and a little bit confusing. And anyway, it is what it is, though, right? So heads up on that. And again, they don't work out nicely in terms of, like you can't do, this thing here that works out so conveniently in rectangular coordinates that the coordinates are the coefficients. I mean, isn't that great? Right? It's a really nice feature of rectangular coordinates. Rectangular standard basis vectors allow me to write any point as a linear combination of these vectors, and the coordinates are the coefficients. Awesome. Right? But not with spherical. Just not true. So heads up about that. One thing is actually very convenient for all of the coordinate systems we're going to be working with, at least the standard coordinate systems we're going to be. So polar, cylindrical, spherical, they're all orthonormal coordinates, orthonormal bases. They're all orthogonal to each other. They're all unit vectors. And that ends up being convenient in various ways. So that's one of the things we like about these coordinate systems. Okay. All right. Pause. Everybody okay? Okay. Off to chapter 2. Now, 2.1 has a lot of little detail devils in it, and again, there's a very limited amount of class time and tough choices and all that, and walking y'all through stuff that you can just read, lots of just sort of definitions of terminology and observations that should have been made back in high school that a lot of high schools maybe didn't quite get around to. This is relatively accessible and reasonable, readable stuff. So I'm gonna go very quickly through this next couple of pages of notes, but do make sure to go all this thoroughly, read the books, presentation and all this stuff. It is fair game for the course, but again, not going to spend a lot of time on this in class. So first of all, we got to talk about what a function is. So definition of a function. A lot of people misunderstand this. A lot of people think a function is a formula, like it's something that you create with algebra. And very commonly, we do use algebra in creating functions, right? But in general, that's not what a function is. A function is a trio of three things where you have what you might call an input space, what you might call an output space, and what we're going to call here a rule of assignment, which is what very often we think of as the formula. The big idea is for any point in the input space, the rule of assignment has to tell me what is the corresponding point in the output space. So for every input, there's got to be an output. Yes?
Is the reason you call it codomain and not range?
Yeah, well, I actually like the term target better. But the term range, unfortunately, gets used sloppily in lots of other contexts. To the extent that I think I would have to say in some contexts let's see how to say this. There are usages in different contexts that conflict with each other. So not everyone agrees on what the word range means. It's a real problem, right? I just avoid the term because I think it's potentially confusing. I don't know what my listener thinks I meant by that, right? But I think the word target is unambiguously clear, and it's convenient. The word codomain I find it's a little fussy. I think target's a little bit more communicative. So yeah, the terms I'm going to be using are domain and target, and I'm probably going to say formula most of the time because mostly we'll be using formulas. All right. Yeah.
Wait, so by target, it could be like where the values would lie?
Yeah, what set the outputs from the function are required to be elements of.
Okay.
That's right. Absolutely. Okay, so a few examples here, and I know you all have seen functions and everything. Let's real quickly go down to the next definition, and that is the definition of an image of a function. Image of a function is nothing more than just the set of actual outputs, what actually comes out of the function, not necessarily the entire set that they are required to be elements of. But this is the set of the actual outputs. So for example, let's see the contrast here. Here's a function. And by the way, let's note the trio. Domain, target, indicated there with that notation. Very common notation. We'll be using that a lot. Domain on the left, then an arrow, then target on the right. And rule of assignment, aka the formula. Right? So no problem. Real number in, real number out. Whatever number you give me, I'm going to square it. That's what this function is. Notice the set of actual outputs, right? What we call the image, the actual outputs. What comes out of this function? Well, you never get a negative number out of this function. If you're putting real numbers in, right, as indicated by R being the domain, you will never get a negative number out. Give me 2 seconds. So even though the target is all of R, the target is just saying, what are we promising all outputs will land in? I'm promising that they'll all be real numbers. Right? But what are they actually? Well, they are all real numbers, but we can say it even more than that. In fact, it turns out they're always non-negative real numbers in practice. So that's the difference between the target and the image. Is everybody good with that? Yes, sir.
Yeah, I think you kind of explained what I was asking.
Oh, okay.
But
Yeah. So you got to keep these two seemingly related concepts. You got to keep these distinct in your mind. Yeah. Yes.
I wanted to go back up like to the history of students and ask why that's the set of real numbers instead of natural numbers.
Oh well, so the responsibility of when you say target, right, is the responsibility is just that anything that comes out of the rule assignment has to land in that set. Right? Now, every student ID number is, I think they're all integers. Anybody have a non-integer student ID number? Wouldn't that be wild? It'd be silly, but it'd be funny. Right? I'm pretty sure they're all integers, but every integer is a real number. And so, in fact, every output is a real number.
But then you also say it's natural numbers instead of real numbers.
Yeah. And that would be a different function. Yeah. Now keep in mind, the point here is that, so these are different functions because they have different targets, and what the target is part of the definition of what the function is. And it may seem fussy, but I'll show you why this matters in just a minute here. Okay, a little bit more terminology to talk about. So we talk about the image of a function, but you can also talk about the image of a point. And specifically, if you have some input x, if you have some input x, and you put that into the function, right, and you ask, okay, what does the function do? Well, the function is going to produce some corresponding output. Maybe that output is called y. Whatever that y is, whatever that output is, that y is called the image of that input. It's just terminology. It just means output. Image of a function is the set of all images of the points. And then heads up of another little bit of terminology. Given an output, let's see here. We can talk about the set of all possible pre-images. In other words, the set of all inputs that would have given that output. Well, in some cases, for a given output, there's only one pre-image. But in other cases, right, for this output that I have here on the right, there's actually two different x's, both of which give that same output. So both of these points are pre-images, or you might say the pre-image set. For this y, the pre-image is a set containing these 2 points. So you can use the language in different ways. All right. Okay, now y'all can look through these examples. There's different ways that functions can get weird. What we're going to be interested in is the case where, in some sense, everything lines up very nicely. For for every element of the domain, for every element of the target. There's this perfect pairing. Everybody's got a buddy, right? It's nice and simple. No sort of like duplications of outputs. No failures to hit an a candidate output, right? No funny business, right? So notice in a case like this, the function is invertible, what we call invertible. This is extremely important. Y'all did some of this in single variable calculus. You talk about like inverse trig functions. You're computing the derivatives of inverse trig functions. It's very useful. It can help you do integration, right? There are integration methods that come from that. Well, you can't talk about inverting a function if it's not invertible, right? So whether a function is invertible or not, in other words, whether you can take these arrows and sort of turn them back around the other way and have it make sense, matters. Right? So for example, notice that in this case over here, it just wouldn't work. Right? This is not invertible. If I have a point here and I want to ask, if I invert this function, what would be the corresponding, where should this go? Well, should it go there? Should it go there? It's not clear which one it should go to. Do I get to pick? No. Right? Nothing arbitrary. So this function is just not invertible. So invertible means this picture right here. So now again, who cares? Well, let's think about these cases right here. I mean, people like to talk about square root as being sort of the opposite of squaring. Well, you got to be careful about it. This function right here, that's not invertible. It is simply not the case that for every output there is exactly one corresponding input. Some of the elements of the target here have two preimages. Some of the elements of the target here have no preimages at all. Right? So that's a problem. You can't invert that function. So this function right here, that casually, sloppily, we might be tempted to call the exact same function because look, the formula, come on, man, the formula is exactly the same. Okay, well that's, I guess, but very importantly, this G that I've got defined here, this is invertible. For every element of the target, there is exactly one corresponding element of the domain. Every target point has exactly one preimage, and thus I can invert it. Yeah.
For f of x equals x squared, would that fall in the category of binary?
You talking about this f up here?
Yeah.
Correct. It's neither injective nor surjective, right? But the more to the point, it's not invertible.
Yeah.
Exactly. Yeah. Right. Okay, so because that is invertible, I can talk about the inverse of that function. Here's the inverse. This is what we call the square root function. And let me remind you, this symbol means positive or non-negative. Right? But that symbol is specifically related to this being the inverse of exactly this, what you might call the invertible square function. Okay, yeah.
So anytime we invert, it's like the domain of the inverse going to be exactly the same sign as the codomain.
Yeah, the domain of the inverse is the target of the original function and vice versa. Yep, totally. Absolutely. Okay, here's another example. I'm going to let y'all read this one. I think it's pretty readable. This will, by the way, assume that you're good to go on some trig that might have been kind of swept under the rug when you were in high school. I don't know. Every course is different. I don't know. Right? Maybe not. But do be aware. The point relevant to us here is that this function, where you allow all real numbers in and you would accept all real numbers out. Right? If you say that sine is a function from R to R, that's not invertible. But if you restrict the domain and target like so, that is now invertible. This is what I like to call the invertible sine function. That's invertible. Its inverse is what we call arcsine. Right? And then let me wave my hands real quick. Now you might like to think about this in terms of the graph. which is fine, I suppose. Right? But let me remind you, how sine is defined in the first place is from the unit circle. And I think this is a pretty good way to think about it. These are, for these values of theta, there is exactly one corresponding y, and furthermore, for every one of these values of y, there is exactly one of these corresponding values of theta. Right? So I always think about arcsine in terms of the unit circle. Always is an overstatement. This is my favorite way to think about the arcsine function. Okay, a little bit of terminology. I think this is very readable. Give this a look. Make sure you know these terms. It is common that we'll talk about real valued functions or vector valued functions, that kind of thing. It's just a reference to how many different variables come out and whether or not those might be better understood as being perhaps a vector. Okay. All right. And then this example here is just kind of for fun. We talk about, multivariable vector valued functions, and sounds like it's pretty abstract stuff. Ooh, multivariable vector valued functions. It sounds sophisticated, and who would ever encounter such a thing? Walking down the street, right? But in fact, it's not rare. So I like to point out that the most trivial of water cooler conversations, right? Talking about the weather. You are talking about a vector valued multivariable function because the weather depends on where you are, longitude and latitude. Don't forget altitude. You may or may not be at sea level. You may or may not be at the surface of the earth. It might be up in the air. Who knows? And when, right? The weather is not a constant, right? It changes with time. So all of these are implicit in any conversation about the weather. And then when you're talking about the weather is not a number, right? The weather it's not, 4 outside, right? There's a lot of things to say about the weather. There's temperature, but don't forget about humidity. I'm from Houston, right? Humidity is a big deal, right? And makes a tremendous difference in how you experience the weather. So that's important. Barometric pressure, important for understanding certain things about, rain and stuff like that. Wind speed, obviously, right? So there's a lot to say. You get a lot of outputs for a corresponding lot of inputs. This is a vector valued multivariable function. Does that make sense to everybody? So don't think of this class as being about abstruse stuff that that only appears in sophisticated circumstances. Not so. Okay. How to visualize functions. Part of the problem of how to visualize these kinds of functions is that when that question comes up in a single variable context, right? When you're doing single variable, high school calculus, right? High school anything, almost certainly. Every picture they draw is a graph. Practically, with a few counterexamples, but practically every picture they draw of a function, they draw the graph of the function. This creates this dependence, right? Students have this natural instinct at this stage to look at any subsequent picture they see and assume that it is a graph. And very importantly, it's not going to be. Graphs have some, but very limited utility in doing multivariable calculus. They're on the table, right? We are going to use graphs, and they are useful. But we are absolutely positively going to have to use other constructions that are not graphs. They don't behave like graphs. They don't have calculus that is reminiscent of that of graphs. They're just totally different, right? So please disconnect, if you could, the idea of a function from the common picture that you've seen called the graph of that function. These are separate things. Now, what I have in the box there is a bunch of formality as to exactly how to write down the definition of a graph, but I don't think that's you look at it if you like, but it's not going to be particularly helpful to us. So what I want to do is just get down to where the rubber meets the road. Let's see some actual examples. So the big idea, and again, you've seen this before, for every input x, right? You list that x coordinate first. You take that x coordinate, you put it into the function, you see what comes out. That gives you a y. That's your second coordinate. You then say, okay, I want to look at the point in the xy plane where x is the first coordinate and y is the second coordinate. And that then gives you, for that x, given its corresponding y, that gives you this corresponding point, x comma y. The graph of the function is the collection of all such points. Does that look familiar, right? I mean, you've probably seen a million examples of these kinds of things. You may or may not. It may have been a long time, right? It might have been middle school. I don't know. But it's probably been a very long time since you thought about exactly what is the construction that we use. You give me a function, and then there is a corresponding picture. Right? So the particulars of how to take a function and produce a picture, you might not have thought about for many years. But this is that process. And notice you can do this in higher dimensions. Right? So here, let's look at this function that has two input variables. Check it out. The domain, R2. Both x and y are now inputs for this function. Right? All right, well, here's the thing. For any given input, that now being a point with two coordinates, x comma y, it's not just a number, it's now a point, or a vector, suit yourself, that is the input to this function. Well, we're going to copycat, we're going to list those first. We're going to see what the corresponding output is from the function, right? You take the x and y, you plug into the function, you see you get some value z. We're going to make that the next coordinate, right? And then I'm going to say, okay, where is that point? X comma y comma z, x and y being the input variables, z being the output variable. We then have that point where z tells you how much you went sort of up to get to that point. Is that cool? Yeah.
So you have to know the function for it too.
Oh yeah. If you're gonna draw the graph of a function, you have to know what the function is. Absolutely. Okay. So yeah.
Does the domain and codomain have to be the same size for it to be invertible?
Nope. For it to be what now?
Invertible.
Oh,
you go from R3.
There's some nasty questions, and I totally understand your question. It's tempting to say yes. Technically, there are some obscure weirdo counterexamples that show that technically it doesn't. But that's not going to be something that we're going to... Those are really weird counterexamples. So generically, you would expect, they would need to be the same dimension. Okay, so again, the graph is what you get when you look at all possible inputs and go through this process. Look at all the inputs, look at all the corresponding outputs, smash those input and outputs together to make a point in this case 3 dimensions, and then look at all of those points. Okay. All right. Now, here's a couple of different takes that you might like, right? One take is that given a function, the graph is the set of solutions to the equation that you get when you choose to give the name, say, y, to the output values from that function. Right? So you come in with some function f. By the way, there is no law that says that just because you have a function called f, for which you have a formula f of x, there is no law that says you have to call that y. You don't have to call that y. We choose, right? Free country. We choose, all our own free will, to call it y because we use the graph a lot. We're accustomed to using graphs, right? But that's not because we have to. We don't have to. We chose to do that. That creates an equation, and the graph is the set of solutions to that equation. So that's one point of view. Here's another point of view. You can think of, in some sense, a little bit loose and sloppy, but in some sense, it's like the domain is like this. Maybe over here, the domain is this entire sort of XY plane. And then the function tells you how far to push upward from points in that domain, right? And so this is a nice point of view on why are graphs of what dimension? Well, why is the graph of this function f up here? Why is this graph a curve? Why is it a one-dimensional thing, namely a curve? Well, it's because we started with a one-dimensional domain and every point just kind of got pushed up by different distances, right? Why is the graph of a function down here, function of two variables, why is this graph two-dimensional? Well, because I started with a two-dimensional domain and every point gets kind of pushed up by some amount, different amounts, but so therefore we get a two-dimensional surface. Out of time. We'll draw the line right here for today. See y'all on Wednesday. Don't forget, attendance quizzes starting on Wednesday. Announcement email coming out tomorrow.
Thank you.
Yeah, see you.